Morning, everybody, and welcome back. So we are going to continue this discussion of a time-independent perturbation theory, which will also be relevant for the second midterm. And today we are essentially going to look at examples on how we can calculate things. We are going to look at how we can set up these contributions in a diagrammatic form without explicitly going through the diagram rules, which we will pick up next week. But this week, we are going mainly to practice, and we're going to look at the equations, and we are going to bring back that simpler example which we had last week, and which we also corrected yesterday. So this is essentially the topic, and the weekly exercise here, one of the exercises is essentially deriving Breuer-Wigner and Rayleigh-Schrödinger perturbation theory. So let's switch to the whiteboard. So what we did yesterday was to derive the expansion for Rayleigh-Schrödinger perturbation theory. And what we ended up with was a compact expression for the correlation energy, which I'm just going to restate now. So this correlation energy, delta E as we called it, and we call it delta E0 to distinguish it from the one which we had from full configuration interaction theory. So this is now defined in terms of the exact energy for the ground state, minus this epsilon zero, where this epsilon zero is now the energy based on the non-interacting part of the Hamiltonian acting on the ansatz for the ground state. So we have a basis, which is an eigenbasis of this operator H0. And this epsilon zero, in our case, is going to be given by the sum over all the single particle energies up to the Fermi level, where this operator, just a quick reminder, is now a sum over the one-body operators. So this has a sum over P, and we have an H0 with XP. And this H0 acting on a state P gives us an energy epsilon P times P. So this is as before, we have what we have been calling a computational basis, which is orthonormal, which we then use to build a many-body basis, which follows, which also is orthonormal. So we have this basis of phi I of phi j, which is given by Kronecker delta. So what we could do then is to rewrite this correlation energy in terms of the interaction piece only. So we have a perturbative expansion in the interaction. And the expression which we had, irrespective of whether we dealt with the Breuer-Wigner perturbation theory or Rayleigh-Schrödinger, was given by this operator Q for the excluded space. We have the exact energy minus H0. And then we have an H of I. And sorry, not H0, but we had this term. Let me just bring up the correct one here. So we have this term omega, which we then put to a specific value. So this is Q, and then we have H, and then we have omega minus E0 plus HI. And now this is to the power of N multiplied with phi 0. And then we could specialize this to either Breuer-Wigner perturbation theory or Rayleigh-Schrödinger. So in Rayleigh-Schrödinger perturbation theory, we put this omega to be equal to epsilon 0. And in Breuer-Wigner perturbation theory, so this is RS. And in Breuer-Wigner, we had omega equal to the exact energy. So yesterday, what we did was to look at the different terms in Rayleigh-Schrödinger perturbation theory, which we then rewrote as a regrouping of this expression here, the one you see here, in terms of orders of H1 or HI. I've been calling it H interaction, so I should say HI. So this was then given in terms of a regrouping of the energies, where we had terms I equal 1 to infinity in principle, and then we have a delta E of I. And this delta E of I to first order was simply given by phi 0 of HI of phi 0, which means that we recover the reference energy, which is now given by epsilon 0 plus this delta E1. And then we looked at in more detail, and this is where we're going to start today, we looked at the second order term. And the second order term, when we now write it down, it's given by HI, and then we have Q. So in Rayleigh-Schrödinger perturbation theory, it went like epsilon 0 minus H0 multiplied with H of I. So these are all operators, and phi 0. So later, through examples, we are going to look at what this looks like in third order, in fourth order, etc. So let's now look at the specific, not a specific system, but a specific operator HI. So we remember then that H of n, normal order with respect to a given reference vacuum, was given by the reference energy plus the operator F of n plus the operator V of n, and where this F of n was now given in terms of a one-body operator, where we summed over P and Q. We had an integral of Q, and then we have an AP, AQ. And just to remind you of how we wrote this out, this F, this is given by the integral for the one-body operator H0. So we should put hats on this one as well. And in case the basis we have chosen is an eigenbasis, then this first integral is different from 0 only if P is equal to Q. And then we had the next term, so I'm just quickly repeating here, which we also call the U-Hartree-Fock. And this term here was nothing but the sum over all the states below the Fermi level. So this is the mean field. So we have P of J, of V, of Q of J, anti-symmetrized. And in our case, when we are going to look at specific contributions now, we are going to assume that the basis we use is not a Hartree-Fock basis. If we use a Hartree-Fock basis, we have to be a little bit careful, because then we would need to include this term as well. Okay, so because the states which we are going to get will be particle Hall states. And in case we have a Hartree-Fock basis, then this term, which you have here, is not necessarily equal to 0 in case of a Hartree-Fock basis. So if you have a state A and I here, then this piece here is set to 0 from the Hartree-Fock calculations. But that means that this term is not necessarily equal to 0. Okay, and then we have the next term, which is the interaction piece. And that is simply given by the standard two-body operator. And this is where we will stop in this course. So we are not going to deal with the three-body interactions or more complicated ones. And then we have an AP, an AQ dagger, AS, and AR. So what we did yesterday was actually to start looking at these expectation values to second order in perturbation theory. So let's look at this from a more diagrammatically / physical point of view. Because what we end up with then is to calculate this specific term, and then we are going to have F of n plus V of n, and then we have this operator Q divided by epsilon 0 minus H0 times F of n plus V of n multiplied with phi 0. Now, the term with the reference energy is obviously 0 because we are linking with states Q, which are not included in your model space. So if we now look at this from a more, I would say, pictorial or diagrammatical or physics point of view, what we can do now is to set up a diagram or figure, actually. So you could now think of this if we now follow the kind of notation which we have seen in the textbook of Shavit and Bartlett, which I think is a very kind of physical, intuitive way of looking at these processes. The way we can now look at this is as follows. So we have an interaction piece here. We have the two-body interaction plus a one-body term. And we leave this unspecified. I'm not putting arrows because I'm not looking at the specific contribution. So then we have this operator, which I'm now, this F, which I'm just going to leave like this box. So this is a one-body operator. So we have a two-body operator plus a one-body operator. Then we start with phi 0. And the way we can think of this now, if we go back to the expression, is that these operators now act on the ground state and produce an intermediate state. Then this intermediate state here is then acting again, the interaction is acting again on the state and brings us back to the ground state. So you can think of this as an intermediate excitation where we now have an operator which acts on a specific state of the system and then brings us into an intermediate state. So we have an intermediate state here. And then this intermediate state gets de-excited and brings us back to the ground state. Now, you can interpret this as a kind of physical process where particles are scattering, they collide, or there are some kind of reactions. The system lives in an intermediate state, which typically is a state which exists within the Heisenberg uncertainty relation, and then it decays back to the ground state. Now, when we are dealing with this perturbative expansion, what we in principle do when we sum to infinite order is that we will have an infinity of such excitations. This is one way of looking at it, which has been very popular in many-body physics, but also in quantum field theory. So the ideas in quantum field theory has been to recognize some of these physical processes in terms of diagrams, and these diagrams can then be given a physical interpretation. Now, when you think of perturbation theory, if you now go back to the equation which we have here, what we are doing now, mathematically, is just a resummation of the contributions to the energy by a perturbative expansion. So mathematically, this is nothing but just a rewrite of the equations so that we get things which we can calculate through approximations, and the approximations which we will deal with are approximations in perturbation theory to a given order. Alternatively, we can leave out specific types of excitations. That's a truncation. When we come to copper cluster theory, we are going to limit ourselves to two-particle, two-hole excitations. But then we will sum those two-particle, two-hole excitations to infinite order. So I'm just trying to wire your brains towards a way to think of these expressions mathematically, but also physically. And one of the reasons why these many-body approaches have been so popular is that you can look at different diagrams or contributions. So this will be a contribution which we rewrite in terms of a diagram. And then you can give to that specific contribution a physical interpretation. And what we will see then when we run the calculations here is that if we take these two operators here, that is going to produce an intermediate state of the two-particle, two-hole type. So that means that we have a perturbation of the system where we excite two particles above the Fermi level, and then these particles decay back again to the ground state. Similarly, this one is something which we can then interpret as a particle-hole excitation of the system. Now, mathematically, you would need to sum this to infinite order, because you can think of the particles interacting with themselves an infinity of times within the Heisenberg uncertainty relation constraint. This is the same thing. So when we deal with the many-body formalism in the number representation, or second quantization, as we've been calling it, then the contribution to the energy is given by an infinite amount of particle-hole excitation. If you instead look at this in configuration space, the interpretation then, when you solve the equations, is that the particles interact with themselves an infinity of times, producing a finite energy for the ground state or whatever kind of state or observable we are interested in. So I'm just trying to guide you along a way by which we can put in some physics interpretations, but in a certain sense, these two-particle, two-hole excitations have to be summed to infinite order. So every type of correlation has a representation in terms of diagrams, which in some cases can be summed to infinite order and can serve as a useful approximation to a many-body system. So like in nuclear physics, this kind of particle-hole excitations are very important because they renormalize the short-range part of the nuclear force. In atomic physics and condensed matter physics, we have long-range particle-hole interactions, excitations, because the Coulomb interaction has an infinite range. So we need to renormalize that part in order to do perturbation theory. Because in principle, if you were to calculate this term here for the electron gas, where we found, in the electron gas, we found this contribution. But if we don't do anything with the Coulomb interaction, this term will diverge for the electron gas. So order by order, there will be diverge, but when we sum to infinite order, particle-hole correlations, that will renormalize the long range of the Coulomb interaction. In nuclear physics, on the other hand, you have a short-range interaction, which is very repulsive, and you have to renormalize that repulsiveness, because else, if you calculate individual matrix elements like this, they will be immensely large, and you cannot do a meaningful perturbative expansion. So there are many such approaches, and this often gives a kind of a physics language, which is pertinent to the specific field. And sometimes it can be difficult to penetrate because there's a lot of jargon. So when I give this kind of physical interpretations, you have to treat them with a grain of salt, because in principle, what you're simply doing is a reorganization of your many-body expressions for the expectation value of the energy. But then it's very tempting to give this a physical interpretation, which is also something which increases your intuition about specific processes which take place. And for some cases, you will see that the interactions favor two-particle, two-hole excitations, because there may be strong pairing correlations, like in nuclear physics. In other cases, it favors particle-hole interactions, like in atomic physics or in condensed matter physics, where you have the long-range part of the Coulomb interaction. So when people deal with these methods, there are different approaches to what kind of diagrams you would focus on. But let's now, after this kind of warning, we're actually going to dive into this kind of more sloppy language where we interpret these diagrams as physical processes. Okay, so let's look at some of these contributors, because yesterday we looked at the case where we had this operator here, but let's now just go into more detail and see how we can calculate. So one way we can now set up things is simply to take the Hamiltonian, act on this state, and then we interact again with the Hamiltonian, and then we go back. So if we now look at the two-body interaction, so let's take that. So that means that what we are going to set up now is a contribution to second order, and now I'm just setting up all the term. So now I'm looking at the contribution from the two-body interaction. So I have a sum here over the interaction term, PQRS. So I'm simply plugging this in, this normal ordered part of the Hamiltonian. I have a T, U, V, W. I'm going to calculate my expectation value with phi 0. But then I have now the operators. So I'm plugging in the two-body interaction. So there's going to be a term of AT dagger, AU dagger, AW, AV, and then I'm going to have an AP dagger, AQ dagger, AS, and AR multiplied with phi 0. And then this is multiplied with the matrix elements. I have a TU of V, and then I have a VW anti-symmetrized, multiplied with the term PQ VRS anti-symmetrized. And now I'm just doing one thing, just for the sake of simplicity. So I'm leaving out the term of epsilon minus H0. So this is just, I'm just going to reintroduce it because now I just want to do the contractions here. So let's say, so this is essentially what we end up doing. This part here, when it now acts on the ground state, it produces a two-particle two-hole excitation. And then this part here is going to bring us back to the ground state. So that means that this has to match the two-particle two-hole intermediate state which we made. So let's look at the contractions. And also keep in mind that we have the interaction has a factor of 1 divided by 4. I have 2 of them, so I get 1 over 16. So now we just set up the different contractions here, and then I'm just going to look at the chain of operators. So now I'm going to keep, because the only contractions which I can have are the contractions of this type. So now I'm going to keep this one fixed. So that gives us, these have to be whole states. So this is a delta T, and then with R, and a delta U with S. And these states here have to be below the Fermi level, all of them. So that means that I'm going to get labels I and J. Then what I can do next now is obviously I keep that fixed, and then I can have this one. But then I can also have this one and that one. So I'm going to get a delta VP and a delta WQ, and I have a delta here. I have a delta VQ and a delta WP here. And this comes with a minus sign because I have to interchange two operators. Then, so this gives me two contributions, and the states which we have here, they have to be above the Fermi level. So that is going to give us labels A and B. So what we will get then, if we now look more carefully at this, is that this is going to give us a term which is AB, V, IJ, and then I have a minus, and this is anti-symmetrized, minus AB of V of JI. No, sorry, not this one. Let me just rewrite it. So this is going to be a minus, a BA of V of IJ, anti-symmetrized. And we know that these two are almost equivalent. If I change A and B, I actually get, so if I add this 2, I get 2 of AB, V, IJ. And the way we can think of this, if you think of this as a diagram, then what we get then is that this AB, V, IJ, anti-symmetrized, this is the same as this specific diagram. So I have A and B outgoing, I and J incoming, and J, and then I have the exchange term, plus, and then I have the particle states like this, A, B, and then I have my hole states, I and J. And this is what we call a two-particle, two-hole excitation. So with the action of the Hamiltonian, we have now created a two-particle, two-hole excitation. But let's now look at what, because we do also have to look at the other term here. So if you look at this term, we haven't said anything about that one. Now we looked at this matrix element, but we also have to deal with this element. So it means that if we now look at the calculations here, we do also have this one, which means that there is a additional term which runs like AB, V, sorry, IJ, V, AB, anti-symmetrized. And to see that, if we now look at the first element, we now looked at this element here. So we put in P and Q, which are the particle states, which became A and B. The R and S are given by I and J. There's the states below the Fermi level. But then we also have that T and U have to be equal to I and J. And then we have U and W here, which are equal to A and B. So if we do that, we get a similar anti-symmetrized matrix element, which means that what we get then is an AB, sorry, no, not that way, but we get an AB, or IJ, or B, AB, and now I'm skipping the anti-symmetrization sign, and I have an AB, or V, and IJ here. Now I'm going to get, I have two such terms, which follow from the contractions here. But then the next set of contractions which I need to do is to look at the case where I keep the same two sets here, but now I change AT and let that one go to AS. And then I have this term over here. And that's going to give me a minus sign, one of these. But then you will see that this just turns out to be equal to these equations. And when I order everything here, I'm going to get 4 such terms in total. But then I divide this by 16 when I look at the contractions. So at the end, what this gives us is the following final term. So I'm going to get, without including the denominator, I have 1 divided by 4. The sum over the 8th subscript is replaced by a quadruple sum over I and J. And then I have the IJ, V, AB, and these are anti-symmetrized matrix elements, but I'm going to skip the AS symbol like this. Then what I omitted was the energy denominator. So the energy denominator, the state, the intermediate state, is a two-particle, two-hole state. And this intermediate state is now going to produce an energy. Let's call this energy for the many-body state. This is going to be given by the single particle energies. We have two particle states, and we are taking away the whole states, plus epsilon 0. So this is an uppercase epsilon. The smaller epsilons are the single particle energies, and the uppercase letters are the sum of the single particle energies. And then the denominator has an epsilon 0 minus epsilon m, which then translates simply into this epsilon I plus epsilon j minus epsilon a minus epsilon b. And that means that the final contribution, this delta E2 here, from the Vn term, from the two-body term normalized with respect to the vacuum, is simply equal to 1 over 4, and then I have a sum over AB, IJ, and then I have my IJ, V, AB, and I can write this like the one which we have here. And then I have my epsilon I plus epsilon j minus epsilon A minus epsilon B. Now, when I now look at the diagrammatic representation, and if I go back to the contractions which I did, if I, for instance, take this specific contraction here with that one, if we take a closer look at that one, so let's take this one and this one, just one of the 4 possible contractions which we had. And these are the only non-zero ones. So if we now look at this diagrammatic, possible diagrammatic representation, so what we had, we produce now, and now I'm leaving out this vacuum state. So what we did was to produce a 2-particle, 2-hole state with A and I. We have the interaction piece, and then we have a B, and then a J here. And then at the end, what we were doing then was to link that piece with this piece here with a J, and we had a B here, and then we had the A and the I. And since we are now summing, it's common then to actually bring together. So when we perform the contractions, what we had was a contraction here, which then in the set of contractions which we had would then correspond to this AV with AT. So that is the one which led to this particular one. And then we had the B here, which then would correspond in the diagrams here to the term which we have here, this one, W and Q. And similarly with I and J, they would correspond to this term and the one which you see here. So we would bring these legs together then, when we just bring them like this, and the diagrammatic representation for this specific term is then given in terms of this closed loop here, and where we, since we are summing over the labels, we close the loops, or close the legs. We have an I here. So what we also have done, if we go back to this original figure which we made, if you look back at the expression which we, or this image which we made here, what we have done now is simply to simplify a little bit. We took away the phi 0. We simply focus on this term and that term, and we also took away that one. So when you look at that specific diagram, what you can think of in terms of physical processes is that you have the system prepared in a ground state, you act with an operator on it, you create a new state, then there is a new interaction, and then you de-excite it and bring the system back to the state where you were. So for those of you who are interested in quantum technologies, this is often the way you prepare a simulation on a quantum computer. You would prepare the system in a given initial state. And then you would repeat experiments on this initial state which you have prepared again and again and again. And then the final measurement is the average of all the measurements you made. So if you now look at this diagram, what you can see here very explicitly when you draw a line in between the vertices you would then say that this is a two-particle, two-hole excitation. And that's the kind of language which you end up using by saying that this is a typical two-particle, two-hole excitation of the system. So if we then draw a line here, we would simply say, because we have two particles, so this is a two-particle, two-hole contribution to the energy, to second order. So in principle, you have an infinity of such excitations. Because what we did was simply to reorganize the calculation of the ground state energy in terms of a perturbative expansion. Actually, a Taylor expansion around an energy. Now, if we now look at the other contractions, it's pretty obvious that there are three more. If we just look at the contractions which we did here. So that means that we will have three more diagrams. And let's look at these diagrams as well. So one of the diagrams which we would end up with is the following, because then we interchanged A and B in one of the vertices. So that means that the whole state are just unchanged. So they leave to the left and right. But then the particle states would simply be interchanged now. So that's one of the other contractions, A and B here. So this is to indicate an exchange in A and B, which then stems from the contraction which we did here, this one, where we have interchange A and B. And then you see the pattern here that there's obviously going to be a new one where we leave A and B, but interchange I and J. So there's a next term where we simply draw the diagram like this, where we have A and B fixed to left and right. And then we have the whole states where we now have taken the interchange and where we have I and J here. And then there has to be a final one where we have also interchanged A and B, which is the one which corresponds to the contraction which you see here, the contraction with this one, but then the one where AT goes to S and AU goes to AR. So diagrammatically then, the last term is going to look like this. So I will have an A and I, and then I have a similar loop here, where I now have particle B and J. So this should be I here. Now, what is common, however, is that we just draw one of them. And since we're using anti-symmetrized matrix elements, although this is not fully correct, you would simply draw this one, and you would calculate this one with anti-symmetrized matrix elements. So the only diagram which is often listed in textbook is actually a diagram which looks like this. And then the assumption is that you have to use anti-symmetrized matrix element. And that means that this diagram encompasses all the four diagrams which we have. The alternative is to use this Hugenholz notation, which is less used, which explicitly uses anti-symmetrized matrix elements. And then the diagram would look like this. So we would have a blob here and a blob here. And then we have particle states, A and B. And then we have the whole states, I and J. So as I said, I mean, people tend, probably for aesthetical reasons, to prefer this diagrammatic notation instead of this one, because this can suddenly become very, very compact. So in textbooks, often you will just see this one listed while people actually mean all four diagrams. Okay, so when you're going to draw diagrams, it suffices actually to put up this one. And what we will do next week is to derive the diagram rules so that you can actually read off from a diagram like this one. You can read off this expression which you see here immediately from a diagram. But then we need to set up the diagram rules. And in Shavit and Bartlett, in chapter 4 and 5, they actually derive the diagram rules, but we will discuss them next week. And then we have a very, how to say, physics-driven recipe for setting up contributions in perturbation theory. But keep in mind that these are not actual physical processes. In particle physics, people often think of these as real physical processes. But in principle, you're doing a perturbative expansion in many cases, and then it's the infinite sum of all the contributions which make up the final contribution to unobservable. Okay, so the other term which we left out, which we didn't evaluate, is the one-body term. Now, one of the things which we discussed a little bit earlier, so let us just bring back this image which we had here, is that if we have created a two-particle two-hole excitation, we need to match that with a two-body operator to bring it back. So if we were to create a two-particle two-hole state and let that one interact with the one-body operator, we would not be able to get an expectation value which is different from zero. So if you create a two-particle two-hole state and you de-excite it, you have to go through a two-body operator. So that means that the only other term to second-order perturbation theory is the one which involves the one-body term with itself. And this is going to create a one-particle, one-hole excitation. And this is what we will then just go through after the break. And then we are going to look at an example where we deal with both Bruyère-Wigner and Rayleigh-Schrödinger perturbation theory and see how we can rephrase everything in terms of specific diagrams. So let's now look at the second term, the one-body term. So if we look at the one-body term, then we have a contribution to the energy, which now is going to be defined only by the U-Hartree-Fock term. But let's just set up this operator, and what we end up with now is a sum over P and Q and T and U. And then we have the, and I'm leaving out the energy denominator as before. And then I have the operator AP dagger, AQ, and then I have my AT dagger and AU acting on phi 0. And this is then multiplied by the matrix elements or the integrals P of F of Q multiplied with T of F of U. So this is the expression without the energy denominator. And if we then look at the contractions which are possible, this really limits us to some very few ones. And we see that immediately that the only possibilities are actually these ones. So that means that the P and U, they have to be less than the Fermi level. And then this one gives us a delta Q and T, and that means that we have labels A, etc., B, etc. So this is an I, J, but in our case, this simply reduces to the following sum. So what we get now is a sum over A and I, and then I have my, if I now pick up my contractions, I have P and U, which have to be whole states. So I have an I have my F, I have my A here, and then I have my A and F and I. So if I then bring in the energy denominator, this means that what I'm going to get now is an energy denominator, which is simply epsilon I, which we discussed also yesterday. And that's the final expression. And now we have to be a little bit careful, since we are now interested only in an expansion in terms of H of I. So we are doing a perturbative expansion where we leave out the H0 term. So that means that in our case, if we now look at the operator, let us just quickly remind ourselves of the operator F of Q here. This is simply given by P of H0, which we are not going to include now, plus the Hartree-Fock term, which is P of the Hartree-Fock potential of Q here. And this one is left out. So here, we only consider P of U Hartree-Fock of Q equal to the sum over J less than F of Pj V of Q of J and anti-symmetrized. So if we bring back these elements, we are then going to get, if you look at the final expression, so that this term is now going to be given by AI here. And I'm going to have this matrix element of A U Hartree-Fock of I divided by epsilon I minus epsilon A. And if I then insert these terms, I'm going to get two sums over the states below the Fermi level. So this is going to be equal to the following expressions. I'm just waiting till you guys have written it down. So if we look at this expression here, what we end up with is the following. So we have a sum over A and I, but then we're also going to get a sum over J and K. So we are going to have an I of J, of V, of A and J, multiplied with an I and K, of V and A and K, because we're just opening up and each one of them contains a sum over the single particle states. And this is multiplied with the denominator, which now obviously only acts on I and A. So diagrammatically, what this means now, if we look at the process which we have set up, we are going to have the creation of a one particle, one hole state, A and I. And then we have the interaction piece here, which has a sum over J. And then this gets de-excited so that we go back to the ground state. And then we have an AI here. And then we have the state K here. So this is the way we would read it as a diagram. And then we join these two pieces, this one with that one. And that becomes as a diagram, a one particle, one hole type of excitation. And the interpretation which we give to this is that of a one particle, one hole excitation. But where this one particle, one hole excitation sees a correction from the mean field. Now, if we have performed the Hartree-Fock calculation, then we know that if we also include H0, if we include H0, we have to do that, then this diagram will be equal to 0. Because in the Hartree-Fock case, what we had is that A of the Hartree-Fock Hamiltonian of I is equal to 0. But as it stands here, if we don't include the H0 term, this is not 0. So if we're using a Hartree-Fock basis, then we need to actually look at the whole operator F. So in many-body perturbation theory, if we take this kind of a purist approach and don't use a modified basis, then we have to evaluate terms like this one as well. But it's pretty common to leave them out, simply because you get so many more diagrams. But these are the contributions which we get then to Second order, so if we collect everything, there are actually, if you take all the exchange terms you can have here, there are in total 16 ways of writing this term. Because we have, with the operators, we have every operator, since we now rewrote. So this is a small digression here, because what we have been doing is that we have inserted a Hamiltonian which has been rewritten for the new vacuum. If you were to take the two-body operator only and a one-body operator without normalizing them to the new vacuum and just do the calculations, that means that you would have had to perform these type of operations also with what comes from the one-body operator. You would have gotten in total 16 different contributions, which are then encompassed in this one. So because you can rewrite this one in terms of all the exchange terms, and in total there will be 16. And since you had 1/16 for the interaction, that disappears. But with the Hamiltonian with respect to the new vacuum, this simplifies to a simpler set of calculations. Okay, so what we have now pictorially with anti-symmetrized matrix elements, we have a delta E to second order, which is now given in terms of these two diagrams. So this will be an A and an I, and then a B and a J, plus this term which we have here. And now I'm using anti-symmetrized matrix elements, and I'm just drawing one diagram. But like the first one has actually 4 different contributions. Okay, so if we now want to look at something to a third order, for instance, we can get examples like the following. So I'm just setting up some of the diagrams to third order just as examples. And next week, when we are going to derive the diagram rules, we are going to just look at the diagram, and from the diagram rules, we can set up the analytical expression. So a typical example, which we have to third order, which we can give this kind of physical interpretations, is a diagram like this one. So let's just write it out. So I have an A and a B and a C here, an I, J, and K. So how do we interpret this diagram? So the way you can think of this is now that we create a two-particle, two-hole excitation. Then one of the particle-hole pairs just moves without doing anything. And here we just have a one-particle, one-hole excitation. And finally, we end up with a two-particle, two-hole de-excitation, which brings us back to the ground state. So how could we think of this in terms of physical processes? So let's think of a system where we have 4 doubly degenerate levels, which is actually going to be the system we are going to look in the second midterm. But if you look at this diagram here, the way you can think of this is as follows. So let's now start with a system where we have 2 doubly degenerate levels below the Fermi level, and then we have 2 here above the Fermi level. So what we're going to do now is to assume that we have a system in its ground state. So these are the system here. And now let me just put in these different physical processes, which that diagram could represent. I'm just going to draw these lines here. And then I'm going also to draw the diagram back again. So let's just put the diagram down here. And I'm not putting labels on the lines of the diagram. So if we look at the first step here, let's call this 1, that produces a 2-particle, 2-hole excitation. The way we can think of that is that these 2 guys get promoted up here. So this corresponds to 1. Then we have the next stage, which we call 2 here, which is a 1-particle, 1-hole excitation. So one of these guys stays where it is. So if we look at this stage 2 here, we could now think of these 2 guys here just being left unchanged. So we could now just mark them like this. So they are unchanged. But then I get a new particle hole excitation, and we could think of this one being excited up here. No, sorry, not like that. Not that one. Let me just bring it back here. So this one gets excited up there. And then if we go to the final one, which we mark as a 3, which is a 2-particle, 2-hole de-excitation, then the system is brought back again to where it was. So we can give this kind of interpretation that since perturbation theory is actually an infinity of such excitations, if you look at this type of excitations you have here with the 4 particles in 4 doubly degenerate levels, you could think of this as being spin up and spin down. So there are some specific symmetries which also have to be obeyed. Then this process here creates a 2-particle, 2-hole states, and then it propagates one of these 2-particle, 2-hole pairs into a new state, and then everything gets de-excited and you're brought back to the ground state. And this is again a vacuum-to-vacuum expectation value. So this is the kind of pictures which we can make of physical processes. And when you are dealing with the interpretation of experimental data, this is a very common way of looking at things. So if we now jump into nuclear physics, in nuclear physics, you often have excitations of the pairing type, which can then be interpreted as an excitation of the following type. So let's look at a pairing type of excitation and how we could interpret that using that simple model, but where we now have a 3rd order diagram. So let's deal with that one, and just let's keep this example here. So it's the same physical process, but now we have a different diagram. So I'm going to set up a diagram to 3rd order, which looks like this. So this is one of the many other contributions. And let's stay with this system with 2 pairs. So one could be spin up and one spin down. Now, if we think of this stage here, this creates a 2-particle, 2-hole state. This stage here is also 2-particle, 2-hole state. But what we have now is a new set of 2-particle states of 2H. So this is stage 2. And then here again, we are de-exciting the 2-particle, 2-hole state, which is stage 3. So you could now think of 1 here as us promoting one of these pairs up here. Now, in nuclear physics, pairing is a very strong part of the nuclear interaction, which arises from the short-range part of the nuclear force. And that means that we can have excitations where we don't break a pair. So that means that if you look at quantum numbers like the total spin here will be conserved because this is spin up, spin down, spin up and spin down. The total spin projection is 0. And you see the same thing happens here. So in this state, we actually conserve the total spin projection. And we just excite pairs of particles. So a two-body interaction can have a component which can lead to strong pairing correlations. So strong pairing correlation is also very important for phase transitions in quantum mechanical systems like superfluidity and superconductivity. And in nuclear physics, in a neutron star, we actually expect to have a superfluid phase in the interior of neutron stars. And that is driven by pairing correlations. So if you look at stage 2, what we could think of now is that these dudes down here, they stay in the same place. But then the particle states get promoted to a new state. So this is the new two-particle, two-hole excitation. And then we are just boringly back to the ground state. And this would be stage 3. So this is another way of just looking at these physical processes, where you have some strong pairing correlations. And this diagram is actually called a two-particle diagram. Now, the nice thing is that you can sum contributions like this to infinite order. So there are ways to renormalize this type of contributions. And that means that even if the contribution can diverge order by order, when you sum this to infinite order, you will get a finite contribution to the energy. And this type of correlations are often used to resum some specific components which lead to problems in a perturbative expansion. So you would have a part of the theory which then would contain something summed to infinite order. And then you can make a perturbative expansion on something which hopefully gives a finite and small contribution when you go order by order. But you see the kind of physics interpretation you can make when you look at these processes. So it's not what happens physically, but it's a picture which we are making. And it's very useful when you're thinking of excitations and explaining experimental data. Okay, so what I want to do now is just to move on with another example, but where we now are going to look at a case which is a little bit simpler to deal with, and where we can do Bruyère-Wigner perturbation theory exactly, and we can compare that to Rayleigh-Schrödinger perturbation theory. And that's also going to bring in some diagrammatic problems which we have with Rayleigh-Schrödinger perturbation theory, which we will also discuss in more detail next week. But let's look at the example here. And this is a simple system which we encountered yesterday and also in the lectures from last week. So we are going to look at a system where you can think of this as a one-particle problem. And we have a Hamiltonian here, which is now given by a sum over I equal 1 to 2. And it has a one-body operator, A of I. There's a single particle energy, epsilon of I. And then there is an interaction piece. So this is a two-level system, like the one which we discussed earlier. So we have a strength for this interaction piece. And this sums of I different from J. And they are equal to 1 and 2. And then we have an AI of AJ. So that's the interaction term. And the exact energies are given by an E1 and an E2. So that means that if I act on H of psi1, this is going to be equal to E1 times psi1. So psi is the exact energy. And similarly, if I act on psi2, this is given by H2 of psi2. And then the non-interacting piece, which is given by this part of the Hamiltonian, is now simply given. So the H0 term is going to be defined as this sum from I equal 1 to 2 of A of I, AI of epsilon I. And we are now going to make a basis where we define a phi 1 in terms of A1 dagger acting on a true vacuum. And then I have a phi 2, which is simply equal to an A2 dagger acting on a true vacuum. And in our specific case, what we have then is that if I act with this H0 on phi1, it's pretty straightforward to see that this is going to be given by epsilon 1 times phi1. And similarly, if I act on phi2, this is going to give me epsilon 2 of phi2 here. This is epsilon 2. So it should be pretty straightforward if you just take these states here and calculate the expectation values there. So we have the non-interacting piece and the interacting piece. So this means now that if I'm setting up specific matrix elements for the Hamiltonian matrix, if I now look at phi1 with hi and phi1, so the phi's are the non-interacting solutions, we see that this one is simply equal to the sum of phi equal 1 to 2, and then I have a 0, a1, and then I have an ai of a1 dagger multiplied with epsilon I, and this is simply equal to epsilon 1. No, sorry, h0. This should be h0, sorry. What we also see, if I take this phi1 of the interaction piece with phi1, this is now going to be given by this lambda, and I have a sum over I different from j. And then I have my 0, and then a1, and then I have a aij. So aij, let me just correct this one. Multiplied with a vacuum state. If I look at that one, we know that I is different from j. And if I do the contractions here, the only possible contractions are obviously this one with that one. And since I is different from j, this is obviously equal to 0. And the same happens if I do, sorry, 2, the state 2 here with the interaction piece. So let's do that to indicate that this is an uppercase letter. We see that this one is also 0. And the only term which is non-zero for the interaction is actually the term where now take the cross elements. And we will find this to be equal to lambda. So this is a two-level system. It means that the exact state is a linear combination of phi1 and phi2. So we have then that psi1 is obviously given by some alpha times phi1 plus some parameter beta times phi2. And similarly for psi2. So the Hamiltonian matrix, which we are going to set up then, is actually pretty simple. It's going to be given by epsilon 1 of lambda, and then I have lambda of epsilon 2. Because the interaction piece is 0 when we are in the same non-interacting case. So this is a pretty simple Hamiltonian matrix, and we see that the characteristic polynomial, which we have to find the roots of, is simply now given by, if I now look at the eigenvalue, E1, that specific eigenvalue, we simply have E1 minus epsilon 1 of E1 minus epsilon 2 minus lambda squared equal to 0. And this should be pretty easy to actually find. And if we now focus on this E1 as the lowest lying state, so the lowest one, when we look at the eigenvalue problem, then we have to pick the minus sign. So that means that E1 here is equal to 1/2 of epsilon 1 plus epsilon 2 minus, since we are picking the lowest state, And then we have an epsilon 1 minus epsilon 2 plus 4 times lambda squared. And that is the lowest lying state. Now, what we are going to do later is to perform a perturbative expansion. And then when we now do Bruyère-Wigner perturbation theory, we will see that the Bruyère-Wigner perturbation theory is actually going to give us exactly this equation. And then when we do the perturbative expansion of this term here, or the Taylor expansion, then we will recover Rayleigh-Schrödinger perturbation theory. But let's now look at these details here. And let's do Bruyère-Wigner perturbation theory. So BW perturbation theory. And if I do that, and I plug in the expressions, so I have a delta E, and the subscript 1 here now indicates that we are targeting the lowest lying state. And if I plug in the expressions which we derived yesterday, this should be phi 1. And now everything is given in terms of this interaction piece. So remember that this one is lambda, and it has a sum over I different from j of AI dagger, AJ. And we found that these terms here are just equal to 0 because we've chosen a simple model. Then we have the second order term, and we get a phi 1 of HI. So I'm just plugging in second order perturbation theory as we did before. Then we have phi 2 of HI of phi 1. And this is divided by E1 minus the intermediate energy, which is just epsilon 2 here. Then we have the third order. And now you will see something which makes life much, much simpler for us. And this has E1 minus epsilon 2 squared. And then I have higher order terms. Now, if you look at this term, and also the higher order ones, because we have only one intermediate state. Well, let's just wait a little bit so you get time to write down things. So if you look at this term, and we go back to the expressions which we found for this interaction piece, so we see that this one is just 0 by construction, since we have chosen an interaction piece where we have the sum over I and j, where I has to be different from j. And if we now look at this third order term, and keep in mind that the higher order terms will have these terms to higher and higher orders. So when we go to fourth order, there will be 2 such terms. When we go to fifth order, there will be 3 such terms. So what can you say about this series now? Terminates a second order, right? So that's the only term. So this one is 0. So this has to be 0, and all the higher order terms have to be 0. So the only term which survives is actually this one. And this matrix elements are given by lambda. So I get lambda squared divided by that one. So if I then plug it in, then I will find that this correlation energy for the lowest lying state is simply given by lambda squared of E1 minus epsilon 2. Then I know that this delta E1 is nothing but the exact energy minus epsilon 1, right? And this is now equal to lambda squared of E1 minus epsilon 2, which then, if we rewrite it, is nothing but the characteristic polynomial we want to find the roots of in terms of epsilon, not E1. And that is the same as the determinant of E1 minus epsilon 1 lambda, lambda E1 minus epsilon 2 equal to 0. So what we have seen now is from the perturbative expansion, the Bruyère-Wigner perturbation theory, for this simple case, and we also discussed that yesterday, that we could recover the exact solution with Bruyère-Wigner perturbation theory. So Bruyère-Wigner perturbation theory is nothing but just a rewrite of the same problem which we would get if we solve the characteristic polynomial. Now, as we said yesterday, Bruyère-Wigner perturbation theory depends on the exact energy we are searching, which means that it is a less practical recipe. And that's why people normally use Rayleigh-Schrödinger perturbation theory. So let's look at what Rayleigh-Schrödinger perturbation theory looks like. But before we do that, we can make a diagrammatic interpretation of this term. So if we now think of this term to second order perturbation theory of E1 minus epsilon 2 here, the way we can think of that in a diagrammatic way, so we have this intermediate state, 2, then we have an interaction, which is given by this strength lambda. It's a one-body interaction, and we have a particle in, or state in, and a state out, which is 1 here. So if we stick to the true vacuum, then we have a particle in a state 1, and then we are calculating the expectation value or the transition probability from state 1 to state 1. So this will be in the particle formalism. But we could rewrite this in terms of a particle hole formalism. So in the particle hole formalism, then we would think of this state 1 as our reference state. That means that we would simply then say that there is a Fermi level which goes here. So we would simply put the Fermi level here, and we would treat that state as a whole state, and this as a particle state. Then we can simply rewrite that diagram. So in the particle hole formalism, then we just link the legs of state 1 with itself. So we would get a diagram which looks like this. So we have a particle state 2 above the Fermi level, and then we have simply closed the lines here for state 1. So this is the diagrammatic representation which we would get irrespective of whether we do Bruyère-Wigner or Rayleigh-Schrödinger perturbation theory. Now we are going to look at the Rayleigh-Schrödinger perturbation theory. And now we are going to see things which are a little bit different, because we will get contribution from different orders in perturbation theory. So let's switch to Rayleigh-Schrödinger theory. In that case, E1 is now replaced by epsilon 1. That's the change which we make. And here we must actually pay attention to the possibilities of having third and higher order terms. So let's look at the perturbative expansion or Rayleigh-Schrödinger perturbation theory. So now we are simply just plugging in the expressions which we put up yesterday in terms of the interaction. And we know that this guy here still has to be 0. So nothing happens to first order. But then I get a term which is non-zero of HI. And then I'm going to have a new term here. So if I now do perturbation theory, let's do that to third order. And next week we are going to finalize this one by going to fourth order. And if I now take the phi 1, so this should be a phi 2 here. And I have a phi 2 of HI of phi 1. And this is now divided by epsilon 1 minus epsilon 2. So that's all fine. Then I'm going to look at third order. So I'm going to get the first term here, which will have a phi1 of Hi phi2. But then this first term, which we get, is going to look exactly the same as we had in Ring-Wigner perturbation theory, and that is going to be 0. So this is 2 here of Hi of phi1. And this is going to have a denominator, which is epsilon 1 minus epsilon 2 squared. Now, this term is also equal to 0. And the term which we got in addition to third order, to this term, which we also have in Ring-Wigner perturbation theory, there is an additional term which is also going to be 0. So to third order, we only have a, so this is going to be given by Hi of phi2 multiplied with phi2 Hi of phi1 divided by epsilon 1 minus epsilon 2 squared. And this term is also equal to 0. So to third order, what we get then is that this delta E1 to third order is simply given by the term lambda squared of epsilon 1 minus epsilon 2. So third order doesn't give us anything new. Now there's an interesting case now. If we go back to the Taylor expansion of the exact energy, so the exact energy had the following expression when we now looked at this E1. This was given by 1/2, and I have epsilon 1 plus epsilon 2 minus epsilon 1 minus epsilon 2 squared plus 4 times lambda squared. Now I can Taylor expand the square root. If I do that, if I Taylor expand that one, what I will get then is an epsilon 1, so it's pretty close to what we did earlier, of lambda of epsilon, that's a plus, epsilon 1 minus epsilon 2. And then I get a minus a lambda to the power of 4 of epsilon 1 minus epsilon 3 cubed. And this is an alternating series. So what we see here is that to third order perturbation theory, I have these two terms here. So the total energy here, E1, is then given by epsilon 1 plus this term lambda squared of epsilon 1 minus epsilon 2. So to third order, I agree with the Taylor expansion of the exact result. So that means that next week, when we are going to look at fourth order terms, what we are going to recover then is actually this term here. So that's why you can think of a many-body perturbation theory as a Taylor expansion around a specific energy. And clearly, this series converges if the ratio between lambda and epsilon 1 minus epsilon 2 is smaller than 1, the absolute value. So this is something which can quickly tell you if you have the possibility to evaluate these integrals, that can quickly tell you something about whether perturbation theory makes sense or not. So next week, we are going to wrap up this example. We're going to calculate this term, and we are going to derive the diagram rules. And when we're done with that, we are going to move into another many-body method, which is called copper cluster theory. But we will take an intermediate step and look at time-dependent perturbation theory, which is an intermediate step. And then copper cluster theory is also one of these widely popular methods, in particular in quantum chemistry, but also in nuclear physics. They are widely used as what we can call golden methods for evaluating ground state energies and also excited states. Okay, this is where we stop today. So I hope you see the link between the expansions and the simpler cases, and that these simpler cases can allow you to develop your own insight about the mathematics of perturbation theory.